Welcome to a code report solution video. In this video, we're going to be covering the solution to problem 1 from topcoder SRM 732 entitled Deck of Cards. The problem states you found a deck of slightly non-traditional playing cards. Each card has a value and a suit. The value of each card is a positive integer and the suit is a lowercase English letter. We will use VS to denote a card with value V and suit S. You want to know whether the deck is perfect. A perfect deck has two properties. 1, all cards in the deck are distinct, i.e. no two cards share both the same value and suit. And 2, for any two cards V1, S1 and V2, S2 in the deck also contains the cards V1, S2 and V2, S1. You are given the following data: n, the number of cards in the deck, a vector of values with n elements, the values of the cards in the deck, and a string suit with n elements, the suits of the cards in the deck. And the question asks us to return perfect if the deck is perfect and not perfect otherwise. And note that n will be between 1 and 50, and the values of our elements are going to be between 1 and a billion, so integers will do for this problem. So let's take a look at a couple solutions that topcoder gave us. So here we have two examples. Our first has n equal to 4 and our second has n equal to 3, and we're given our vector of values and our string suits, which represents our cards. So I'm going to line up these suits, the characters in our string, with our values just so it's a little bit easier to read. And we can see that this means that we're going to end up having 4 cards in our first example and 3 cards in our second example. So what this is going to look like for our first example is we're going to have 2 cards of the suit H, H2 and H3, and then 2 cards of the suit C, C2 and C3. And for our second example, we have something similar, H1, H1 and C1. And basically what the problem is asking us is to return whether the deck is perfect. And a perfect deck has sort of 2 properties. The first property is that for every suit has every value. So you sort of have like a complete deck. That meaning that if you had a third card that had the suit H, but the value is 4, and you didn't have a suit C4, this deck would no longer be perfect, and so we wouldn't be returning perfect. But because we don't have that condition, it is perfect. And the second property that we have to satisfy is that we don't have duplicates. So even though this, in our second example, this is a complete deck, it has duplicates, so we're going to return not perfect. And so the way we're going to approach this problem is by storing each of the cards in a map. And so you can sort of think of it like this, and the key for each of our maps is going to be the suit, and the value is going to be the count of the number of cards with that suit. And so for our first example, we're going to end up with a map where the keys are H and C, and as well for the second example, and the values for each of those are going to be 2, 2, and 2, 1. And then all we have to do once we have this map is figure out what are the distinct or unique values in our deck. And then we need to check that the count for each of our suits is equal to that unique number. And if it is, then we know then we have a perfect deck. And if we're violating that condition like we are for the second example, so the unique number of values we have is 1, but we've got 2 cards of the suit H, we know we're going to have a not perfect deck. So that's going to be the algorithm. So let's take a look at our code. So here our function is valid, takes 3 parameters, our integer, our vector, and our string, which represent our cards, and it's going to return a string, either not perfect or perfect, depending on what our deck is. So the first thing we're going to do is declare an unordered map, a hash table. The key is going to be a character, which represents the suit, and the value is going to be an integer, which represents the count of the cards with that suit. So we'll call this M, and then we declare an unordered set, a hash set, which is going to keep track of the unique values in our deck. So we come to our first for loop. What we're going to do is we are going to look at each card, and so we're going to insert into our map for each suit a post increment on our pair. So when you pass this character, which represents our suit, via the bracket operators to our map, that's going to return us a reference to the value so that we can do a post increment. And if the suit doesn't currently exist in that map, it will automatically insert it, so we don't need to worry about that. And after we've done this, we're going to insert our value into our hash set to keep track of the unique values. Note that sets don't contain duplicates, so that's how we will keep track of the unique values. So once we've completed this for loop, we've constructed our hash set and our hash table, and all we need to do is check that for each pair of values in our map, the value is equal to the size of our unordered set. And if any point we violate this condition, we're going to return not perfect. But if we can get through this for loop without violating the condition, we're going to return. So we can make some adjustments to this algorithm to use a little bit more of STL functions. So the first thing we could do is we could get rid of unordered set and instead just construct our hash table, and then after we've done that, sort the values in our vector value, and then use the STL function stood unique, which will, using that and the STL function distance, we'll be able to get the number of unique values in our vector value. And on top of that, we could also use the STL function stood all of combined with a lambda expression in order to return our not perfect or perfect at the end. So let's take a look at that code. So here is our more STL sort of alternative solution. Once again, we're still constructing our hash table at the top and setting it up as we did before. But at this point, we then sort the values in our vector value. We make a call to stood unique, which is going to return an iterator. We then make a call to distance using the iterator we just got, and also using value.begin. And this will essentially give us the unique number of elements that are in our vector value. We can then set up a lambda expression, which we are going to pass unique count to, and then all we are going to do is return unique count equal to the value in our pair from our map for each pair. And then we can combine this lambda expression with our stood all of function, and this will return true if all of the pairs in our map satisfy the lambda. So it's the lambda is essentially saying the size is equal to unique count. So if all of our pairs have a value that's equal to the size of unique count, then it'll return true and will return perfect from our function. Otherwise, we'll return not perfect. And note that topcoder compiles their C++ code with C++ 11, and because we're using an auto in our lambda, that's going to make it a generic lambda, which is only supported with C++ 14. So in order to get this code to compile on the topcoder compiler, you're going to need to explicitly declare the pair. You can't use auto. So the last thing to talk about is the time complexity. So because we're using a sort in this algorithm, the time complexity of this function is going to be n log n. And for our original solution, it's going to be linear because we are only looping over the length of our vector value in our string suit, which is n.
As always, if you enjoyed this video, hit that like button. Make sure to follow me on Twitter for reminders 30 minutes before contests start. You can find all of the code that I use in my videos on my GitHub page. All of the links are in the description down below. And finally, if you want to make sure you don't miss any of my upcoming videos, make sure to hit that subscribe button. Thanks for watching, and I'll see you in the next video.